I forgot to bring the exams, and so in case people are picking up today, so I'm gonna go. I'll be right back.
So, Dr. Tran,
Yep.
I know you said for the MATLAB code we didn't have to change anything below inputs, but we do have to add, right? We do have to add sections to our matrix.
I mean, if you're going off the code that you started in class, like you have to finish that one. But I posted the full complete frame FEM code, and so for that you don't have to change anything below. So the assembly is already all handled for you.
Oh, you posted? I thought you just posted the complete example because I haven't honestly. I'm stressing so much over this modeling class that I haven't started the MATLAB yet.
Yeah. So I mean, the code is configured to do that example, but then you just have to change the inputs to change it to a different problem. So below the inputs lines, you shouldn't have to change anything on that code.
Yeah, because the one we did in class, right? It only had 3 bars, but the one you gave us on homework has 5 bars. So you posted the 5-bar complete code on the. No,
so the complete code is for the 3-bar. It's for 3 bars, and so you just have to change the inputs. And so if you change the inputs, the rest of the code kind of configures itself automatically to do the 5-bar one. That's how we design the code, so that you can just change the inputs. You can have like a 20-bar assembly, and the rest of the code will configure itself based on the inputs. Yep.
Okay. I was under the assumption we needed to add a bar element.
Nope.
Okay, so all I have to do is just complete the code and then enter it in.
Yep.
The 2D trust, that's a different story, right?
The 2D trust you have to develop yourself. So that one you have to just get to do from scratch. But I did post a starter code for that, and so you can use that as kind of like a starting point.
Okay, I'll probably talk to you about that on Thursday.
Okay, sounds good.
How was your weekend, Dr. Tran?
Oh, yeah, it's muted. All right, what's up?
No, just checking in. How was your weekend?
Oh, my weekend. Yeah, my weekend was good. So I got dinner with my parents. That was a nice thing, and yeah, just had a good one. Getting used to daylight savings time. I think that's the main part.
Nice. Yeah, I
Okay,
feel you.
it's 5:30, so let's go ahead and get started. So I don't know. Actually, I don't know if it's still muted. So the volume looks like it's up here, but you know, hopefully it'll be okay. And so if I don't answer you, then just type in the chat, I guess. So how's everyone doing today? Good. Yeah. This week is always challenging just because it's the last week right before spring break, and so I know everyone's kind of just hanging in there by a thread, or kind of some people are kind of already on break, and so I appreciate you guys are kind of already are still here with me. Okay, so the plan for today is we're going to continue our lecture notes on the finite volume method, and so we started talking about that last time, and so we're going to get through that. Okay. Remember, the next homework is due on Friday, so make sure you guys are working on that. And if you have any troubles with the theory portion or the MAGA portion, then just as always, you can just let me know, and I'll always do my best to help you out. Okay. Your final project is almost ready, and so I had created the animation just to show you guys today, but I forgot it. I forgot my thumb drive in my office, but I've decided what the project's going to be about, and I have the final solution already. I just have to type up the specs. And so Wednesday, we're going to start first thing we do on Wednesday is we're going to talk about the final project, what's required of it, just so that you can start working on it if you want. Okay. Technically, you have almost everything that you need to do the final project already if you want to do finite differences. And so, if you want to get started on that, you can definitely do that. Okay, and so I think that's all my announcements. So are there any questions I can answer before we get started? Okay, all right, so let's go ahead and get started. Oh, question. So is the project individual or team? It is individual. And so, so everyone's gonna be working on the same code more or less. And so, you can definitely work together with your friends on that. And when I say work together, it's like I always said, working together does not mean someone has the pom-poms out and just cheering someone on and copying it from them, right? So working together means that everyone's working on the code together, and you work through things together, right? And for sure, everyone's going to write their own final report, and so it's very much an individual project. But I designed it so that you could at least help debug each other, through collaborations if you want. Okay, you can use the Discord server for that as well. Okay. All right, so let's go ahead and get started. And we were talking about introduction to the finite volume method. All right. And so we started talking about finite volumes last time is kind of this new method that we're going to go over that essentially accomplishes the same thing as finite differences. It's just the way that we're going to go about it is slightly different. Okay. And so just like finite differences, the finite volume method is going to be a way for us to solve these partial differential equations using computer code. Okay. And just like in finite differences, the way that we're going to do this is we're going to take a complicated PDE system, differential equations, and transform it into an algebraic system of equations. Okay, just the way that we're going to do it is slightly different. Okay? The big difference between finite volumes and finite differences is that our focus is going to shift. Okay. Okay. And so if you remember in finite differences, we focused all our attention on the nodes. And so we solved for the solution values at the nodes, and then, we went from there. And so instead of focusing on that, what we're going to be focusing on instead is the cells or the volumes in our grid. Okay. And so in 1D, you would have a grid that looks like this, right? And so we have our connected line segments. And so in the finite volume method, we're going to focus our attention on this region over here, okay? And of course, in 2D is a little bit more obvious. So we have our checkerboard pattern here, right? And we're going to be focusing on the cells inside there, okay? And the main mathematical tool that we're going to be using that allows us to form equations over a region of space or over a cell is integration, okay? Okay. And we had just started talking about, how we actually did that last time. Okay. All right. So that's just a kind of a recap of last Wednesday. And so are there any questions on any of this? Okay. All right. So let's go ahead and continue. And so the next topic that we have to go over is this idea of cell-centered finite volumes. And it ties directly kind of with this previous point right here. And so intuitively, it makes sense that, if we're going to be focusing on the regions of space inside our grid, and so if we're focused on the cells, it makes sense that we're going to use integration over these parts, okay? But then that kind of begs the question of, what exactly are we solving for here, okay? Because in finite differences, it was very clear. And so in finite differences, we solved our equation, and what we obtained was a list of solution values. And those solution values were basically the values of our solution at each of the nodes in our grid. Okay, and so I've circled those in red to kind of remind you of that. And so in finite volumes, we're still going to get a list of values, right? So it's not going to be a function. Okay. Right, so we're still going to have a list of values, but their location is going to be slightly different. Okay, and so instead of being located at the grid points of our mesh, right, the solutions that we solve for in finite volumes, you can physically think of them as being located in the center of our cells. Okay. Okay. And so let's take the 1D case again, okay? Because this is the one we're going to be working with first, right? And so here's our typical 1D grid, right? And so we have 5 grid points and 4 cells, right? Okay. And so when we solve the finite volume equation, right, we're going to get 4 solution values here, okay? And so FP solution will be okay. And so it'll be a list of 4 values. And so, just for this case, we'll call them U1, U2, U3, and U4, okay? And so in cell-centered finite volume theory, the locations for these solutions will be in the middles of the cells. Okay. So they'll be just like that. Okay. And so again, we're not solving for the solutions at the grid points anymore. We're solving them at the centers of our cell. Okay. It's a slight shift, and you might think it doesn't make that big a difference, but it'll make a big difference in how we form our equations. Okay, because I want you to make kind of let's make one key observation here. Okay. And so the key observation that we're going to make is that the solution values that we're solving for, they no longer straddle the boundary, right? Because normally when we solve an equation like this, right, and so this is just going back a little bit, okay? And so we would solve for like U1 here, U2 here, U3, U4, U5, right? So that's what we would normally do. When we applied the boundary conditions, it was a fairly simple matter because our nodes directly sat on top of the boundaries, okay? And so it made it very easy to apply the boundary conditions because our node was already right there. And so we just, made our node satisfy the boundary. In finite volumes, we no longer have that luxury. And so, the application of the boundary conditions is probably going to be the part that's most different between finite volumes and finite differences, okay? And so I don't want to get into the specifics of it now because it is a little bit heavy, but hopefully we can get into it later today. Okay, but that is one of the big differences. And so some people think even though if you look at the theory behind it, it is a lot more involved in finite differences, but implementation wise, it actually makes the code. Some people argue it makes the code look a little bit cleaner. Because right now with finite differences, we have to have separate loops. If you think about, like our 2D finite difference codes, we have to have separate loops that apply each of the boundary conditions on each of the sides. And so that kind of leads to like a very long and kind of, complex code. But for finite volumes, all the boundary conditions are kind of baked right into the normal equations. And so you end up with a code that's some people think is a little bit easier to follow because there's just kind of one big loop for everything. But it takes a bit more work to kind of get to that point. And so, there's pros and cons. I think at first, you'll probably hate finite volumes and you want to go back to finite differences, but maybe by the end of the class, you might actually start to prefer it because it makes your code look a little bit cleaner. Okay. All right, any questions on this? Okay. All right. And so that's self-centered FVM. And so I wanted to go over that last Wednesday, but we were just kind of out of time. And so this is the part that we actually did start, which was the divergence theorem. Okay. All right. And so if you remember, from even I guess we talked about it last Wednesday, but divergence theorem was probably mentioned at one point or another in a previous class, most likely a physics class, and it's one of the many integral theorems out there. Okay, because we're going to be working with integrals a lot, and so that kind of naturally makes us want to use some of these integral theorems to kind of simplify our work. Okay. And there's various versions of the divergence theorems, depending on how many dimensions that you're looking at, but they all kind of have the same, goal, okay? And so the key for the divergence theorem is that it allows us to transform one type of integral to another, okay? Specifically, for finite volumes, it allows us to transform a region integral or a cell integral into a boundary integral, okay? Or sorry, a region cell integral. The boundary integral is what we want to turn into. Sorry about that. Okay. And so I'll demonstrate what this means, in each of the different dimensions. Okay. So let's start with 3D. And so in 3D, a 3D region of space is a volume, right? And so the integral that allows us to integrate over a volume is a triple integral, right? And so we have three integrals here. And so that represents a integration over the 3 dimensions. Okay, it could be X, Y, and Z. And our integrand in this case, takes a very specific form. And so the integrand is going to be the divergence of some vector valued function u, okay? Has everyone seen the divergence operator before in a previous class? Like the nabla dot u? It at least looks familiar, right? Okay, good. Yeah. And so what the divergence theorem says is that if you have the divergence of some function like this, you can transform this this triple integral here into a surface integral. Okay. And so I'm going to denote a surface integral by writing 2 integrals with an oval through them. Okay. And so this one right here would be a triple integral. Over the volume. Okay. And this here is a surface integral around the boundary. Okay. Right, and so to kind of give you an example of this, I think that the simplest triple integral that you can do is of a box. Okay. And so if you were to perform a triple integral, it would be an integral that covers the entire volume of the box. Okay. Whereas the surface integral on the boundary would just be integrals over the 6 sides of the box. Okay. That's the triple integral. This would be over the box boundary or box volume, excuse me. Okay. And the surface integral, this only just covers the surface of the cube. And so this would be on the 6 sides. Okay. It's a little bit hard to draw in 3D, but the 2D one I think will be a little bit more clear, right? But the point is that on one side you have an integral that covers the entire cell, okay, or the entire volume, and on the other side you have an integral that just goes over the outside boundary. Okay. All right, so let's look at the 2D version. And so a 2D region of space is an area. Okay, so we're going to have a double integral. And just like above, the requirements for this are going to be that your integrand has to be a divergence of some kind. Okay, so divergence of u, dA. Okay. And on the other side, we have a line integral around the boundary. So this one's a little bit easier to visualize. And so, for a 2D cell, we'll have a square, right? And so the double integral across the boundary, or double integral across the volume, is going to be an integral that spans this entire space that I've blocked off. Okay. Whereas the line integral around the boundary, we just do an integral around the boundary just like that. Okay. Right. And so we kind of, for the right side of these expressions, we kind of ignore what's going on in the middle. And we only really concern ourselves with, what's happening on the edges or what's happening on the boundaries of our cells. Okay. That's the 2D version. I believe we went over the 2D version together last time, but here's kind of it again, just for the sake of completeness. All right. Any questions on this? Yep.
So the line integral around the boundary, that's similar to the control volume, right?
Yep.
Considering everything what's inside, that's why actually consider it.
Yeah, so actually that's a good point. So this has strong roots in fluid mechanics. And so if you remember, when we did control volume analysis in fluids, what we were actually concerned with was what fluids were entering the volume and what fluids were leaving. And the way we actually evaluated that was with the surface integral. And so, you guys have already actually, if you remember from fluids, this is a key concept in fluids because, what we said was that, the transport theorem, if you integrate it over the entire volume, then, we can transform that into just whatever fluids enter and leave. Right? Yeah, so it's the exact same idea. And so that's, that's why finite volumes has strong roots in fluid mechanics. Yeah. Mm-hmm. All right, any other questions on this? Okay, all right, so last thing we will have is just the 1D case. Well, the 1D case is a little bit too obvious that it's not even worth putting down, but it's fun to write it down. Okay. All right, so the 1D case, the 1D form of a divergence is simply just the derivative of the function, okay? All right, and so that's why up here we have some complicated divergence expression, but here we just have a derivative, okay? And so divergence in 1D is just the derivative. Okay, dx. Okay. And so the divergence theorem, right? Here we have an integral over a 1D region. And so we integrate from, point A to point B, right? And so we can think of it, we cover that entire distance between A and B, okay? And so the boundary version of this would just be to evaluate the integrand at the boundaries, okay? And so the divergence theorem in 1D is simply just do the integral, right? And so it doesn't really get much more complicated than that. But you can see here that this expression right here, which may seem like a simple evaluation, right? It kind of follows the same themes as everything above, right? Because phi B and phi A, these are just function evaluations at the boundaries of our 1D domain. Okay? Where the boundaries of our 1D domain are just B and A, okay? Right, and so if you look at the right-hand side here, we don't really concern ourselves with what's happening between B and A, okay? We don't have to worry about that. The only thing we have to worry about is just what's happening at the ends of our domain, okay? So that's why we have phi B and phi A. All right, any questions on this? Okay, all right, so that's trapezoidal rule. And so, so that's divergence theorem. My mind's already kind of think ahead. And so that's the first kind of integral theorem that we'll use, okay? And we'll use it very soon. But the other, we need one more integration rule before we can move forward, okay? And that's known as the trapezoidal rule. Okay. And so the idea with trapezoidal rule is actually quite different from divergence theorem. And so what's going to happen during the finite volume method is that, even with the divergence theorem and even with kind of a lot of our clever tricks that we can use with integration, we're still going to end up with integrals that are very difficult to evaluate. Okay. Okay. And by evaluate, what I mean is, you take the antiderivative and then you plug in the function and everything like that. Okay. We're still going to come up with integrals that are hard to do. Okay. And so the idea with trapezoidal rule is to approximate these integral values to make them a lot easier to evaluate. Okay. Okay. And so that's the kind of the key here. And so the key here is the word I underlined, which is approximate. Okay. And so trapezoidal rule is not an exact method. And so, you can't use trapezoidal rule to expect to get exact answers, but it is very, very convenient. Okay. And here's how it works. And so, and once again, there's 3 versions of this, depending on if you're on 3D, 2D, or 1D. Now I'll start with the 3D version. Okay. All right, so in 3D, we might have a situation like this where we have some function. Okay. And since we're in 3 dimensions, this function is going to be a function of x, y, and z. Okay. And so a lot of people might look at that and you think, oh, triple integral, I have to integrate 3 times. Like, that's like, what a pain, right? That's a big pain. And so another way to do this is that instead of performing the antiderivative, which I think most people will agree is the worst part of doing integrals, okay? What we can do instead is we can take the integrand, we evaluate the integrand at the centroid of our domain, okay? And we multiply it by the domain volume, okay? All right, so this f of xc, yc, zc, this is the integrand evaluated at domain center. Okay. And this V here, this is the volume of our domain. Okay. All right. And so with trapezoidal rule, you don't have to perform any kind of integration at all. You don't have to take any kind of antiderivatives. And so you just take your integrand, whatever it is, you plug in a certain value of x, certain value of y, certain value of z, where those values are the centers of your domain. Okay, and you just multiply by the volume, and that gives you your integral. Okay, it may not be exact, but at least it's convenient. I have an example of this in 1D just so you can see, but in 3D it's a little bit hard. And so we'll hold off until we do the 1D case before you can see it in action. All right, any questions on this? Okay, all right, so let's look at the 2D version. And so the 2D version, what we have is a double integral. Okay. We have a double integral over a function of x and y. So we have f of x, y. Okay. we multiply it by the function value at the centroid. Okay, so just like in 3D, but here in 2D we only have two variables. Okay, and instead of multiplying by the volume of the domain, we multiply by the area. Okay. All right. And so that's the 2D case, and then let's do the 1D case, and then we'll do an example in 1D just so that you can see it in action. Okay. All right, and so in 1D we have an integral that goes from a to b of a one-dimensional function, so f of x. Okay. And so what we can do is we can evaluate the integrand at x sub c, okay, which is the centroid of our domain. And here we're gonna multiply it by the length of the domain. Okay. All right, and so this xc right here, this is the centroid, and so xc is just going to be the midpoint between b and a, and so it's going to be b plus a divided by 2. Okay. And the length of the domain is the length over which we're integrating, and so the length here is just going to be b, which is the upper bound, minus a, which is the lower bound. Okay. All right, and so you don't have to do any kind of anti-derivative at all. You just take the integrand, evaluate it at the centroid, and then multiply it by the size of the domain, and then that's an approximation for an integral. Okay. Okay. So any questions on this? Okay, so let's do an example to kind of show you this in action, okay? Because it seems kind of crazy, right? And so it's one of those things that are, why didn't they teach us this in math, before? And so I want to prove to you that it actually works. All right, so let's take the integral. We'll take the integral from 6 to 10, okay, of the function 4x plus 6. Okay. They didn't want to give you an easy life. I can. Yeah, I can relate with that. I remember in high school when I was taking calculus, for the first time, my professor, my teacher, taught us how to do derivatives with the limit, right? And so you take a function, you take the function x plus dx, you divide by dx, and you take the limit as dx goes to 0. It wasn't until we did this for 2 months until he taught us the power rule of derivative is the easy way, and it's like, why didn't you tell us this before? It's like, that's how you're supposed to learn it. That's derivatives. Okay, and so let's go ahead and evaluate this using the trapezoidal rule. Okay. And so I admit, in 1D it's a little bit silly, especially with the function like this. Because it's not that hard to actually integrate. But I did want to show you that it actually works. Okay. All right, so first thing we're going to compute is xc. Okay, so xc is going to be the centroid between these two. And the centroid between them will be 10 plus 6 divided by 2. And so that's going to be 8, right? So that makes sense. And so the midpoint between 6 and 10 is going to be 8. Meanwhile, the length of the domain between 10 and 6 is going to be just 10 minus 6, which is 4. Okay. Okay, and so if we perform this integral, we have our integrand here, and so our integrand is 4x plus 6. Okay, so what we're going to do is we're going to evaluate this at the centroid. Right? And so for 4x, we're going to put 4 times 8, where 8 is xc, plus 6. Okay. And so this right here will be f at xc, okay? And then we're going to multiply by the length, which is 4. Okay. And then we perform that arithmetic, we end up with 152. And so that's our approximation of this integral using the trapezoidal rule. Okay. Now let's try this the normal way. And so the normal way, we have integral from 6 to 10 of 4x plus 6 dx. Okay. our first step here is to compute the antiderivative. And so the antiderivative is 2x squared plus 6x, right? And we're going to evaluate this from 6 to 10. Okay. Okay, so let's go ahead and perform this integral the normal way. And so we have 2 times 10 squared plus 6 times 10. Okay. And it's going to be subtracted from 2 times 6 squared plus 6 times 6. Okay. And so if you perform that arithmetic, what you get is 152. Okay. And so hopefully this shows you that the trapezoidal rule is legit. Okay. And so you don't have to do the integration all the time. Okay. And so of course, in this case, it did end up being exact. And so, we didn't see any differences between trapezoidal rule and normal integration. But in general, you can expect there to be some kind of error between the trapezoidal rule and normal integration. Okay. It was only just because the 4x plus 6 is such a simple function. And so this will work, no matter what, okay, for the trapezoidal rule. So you'll get an exact solution here. But if we did something more complicated, something with sinusoids or exponentials, then you might see some differences in between them. But you'll still get pretty close in most cases. All right, and so once we start talking about the finite volume method, we're going to use the trapezoidal rule to help us evaluate some of the integrals. Okay. All right, any questions on this? Okay.
Yeah, quick question. I guess how would you know how far off you are?
Yeah, it's a good question. So the question is, how do we know how far off we're going to be? So a lot of that depends on the integrand itself. And so the rule for trapezoidal rule is that if you have a linear function, then you're going to produce an exact integral. And so here we have a linear function, and basically the further away your function is from being linear, then the more error you're going to have. And so if you have like a quadratic function, a cubic function, fourth order function, then that's going to be even worse. And then if there's other types of functions too, so there's like logarithms, there's sinusoids, there's exponentials, and so a lot of those are going to have some error.
I guess is there a way to know how much that error is?
There is. They involve Taylor series, which I think no one wants to see again, and so yeah, I'll leave it at that. If you are interested, I know, or at least they should. There's a general engineering class called EGME. I want to say it's 413 or 411 or something like that. And so that class is called numerical methods. And so they should go over this. Trapezoidal rule is one of the core, it should be one of the core lessons in that class. And they go over, how to estimate the error for these methods. All right, any other questions on this? Okay. All right, so now that we've learned divergence theorem, and now that we've learned trapezoidal rule, let's go ahead and put them together. And so let's discuss, the actual finite volume method. So this is the finite volume method. Okay. And so this section of the notes is going to be, similar to how we first discussed finite differences, right? So remember when we first discussed finite differences, we took our conservation equation, applied finite differences, and we obtained our algebraic equations, okay? So this is going to be the same, but for finite volumes. And so our starting point, of course, is going to be our general conservation equation, okay? But I'm going to put it in an interesting form. And so I'm not going to use the straight up derivatives like last time. I'm going to put it in terms of, in a form that has the divergence. Okay? All right, so let's start with the unsteady term. So the unsteady term doesn't change because it's our only time derivative, okay? Next, what we have is our convection term. Okay. And so this right here is convection. Okay. All right, next we have the diffusion term. Okay. And of course, this is our source term. Right, so that's our full conservation equation, but it's in, you know, I didn't expand out the derivative, so I kind of just compressed them into one. Okay, and so you know, again, the reason I'm doing this is just it makes the integration a little bit easier. Okay. All right, so first thing I'm going to do is I'm going to assume steady state, and so I'm not going to consider the unsteady term. Okay, but we will come back to it, and so when we talk about unsteady finite volume equations, you know, we'll bring this guy back. Okay. Okay, and so if we assume, you know, let's assume for a second we are in 2D. Okay, and so if we assume we're in 2D, let's take this equation and integrate it over a 2D cell. Okay. And so let's go ahead and do that. And so on the left-hand side, without the unsteady term, we're just going to have a double derivative of the divergence of v with an arrow times phi. Okay. Where v with the arrow, this is our convection velocity. Okay, we're just putting it in vector form. And on the right-hand side, we have double integral over the area of our diffusion term. Okay, dA plus our source term as a you know, integrated over the same area as well. Okay, and so we double integral of q dA. All right, so first thing we see, our first thing we're going to do is we're going to notice that these two integrals that I've underlined, you know, we can apply divergence theorem to these. Okay. And so let's use divergence theorem to transform these 2D region integrals into boundary line integrals. Okay, so this first integral here is going to transform. And so instead of a double integral over the region, we're going to have a single line integral around the boundary. Okay. Okay. And the integral that pops out is the line integral of phi multiplied by the convection velocity multiplied by the dot product with the normal vector ds. Okay. And then same thing for the diffusion term as well. And so for the diffusion term, we have line integral around the boundary of k multiplied by the gradient of phi dot product with n ds. Okay. And then for the q, the source integral, and we're just going to keep that the same. All right. Okay. And so this is where we are in the you know, in the integration. All right. Any questions on any of this so far? Okay. All right, let's clarify some of these terms a little bit, okay? Because remember, this term right here came from convection. Oh yes, the equal sign gets carried over. Thank you. I forgot about that. Okay. And this guy is carried over from diffusion. Okay. Let me clarify what these two terms kind of physically mean, because I think that's kind of the whole key to the operation. Okay. And it would really help if you kind of try to remember, you know, what we went over in fluid mechanics. Okay. Okay, so what I want to focus on, and I think it's a little bit easier to visualize with convection, is this term right here. Okay. And so this v dot n, you know, maybe I should have defined n first. So n here is some outward facing unit vector from our surface. Okay. And so we have a boundary like this. Okay. Then the n would just be a vector that points, you know, on the outside of the domain that's perpendicular to the domain surface. Okay. Okay. And so to kind of properly interpret this, you know, it's kind of important to remember, you know, what a dot product does in this case. Okay. And so in this case, we're taking the dot product of the velocity, and what that dot product is going to do is going to take the component that crosses through the boundary. Okay. And so let me draw you an example. And so, you know, for this square right here, you know, let's say that we have a velocity field that looks like this. Okay. Okay. So this is v. So this is v arrow. Okay. So that's the velocity field. Okay. If we take this velocity vector, okay, and we kind of bring it out here, right? We can break up this velocity vector into two components, right? And so we're going to have a Vx as well as a Vy, right? And so any vector, you can always break it up into its components. And so, you know, in this case, I picked X and Y, you know, but you can break it up into any components that you want. Okay. And so let's take this kind of drawing of V and then match it up with the definition for the dot product I have below. Okay. And so remember, the dot product takes the component of V, the component of the velocity that actually crosses over the boundary. Okay. And so if we're looking at this right face right here, this right surface, you know, we can see that the normal vector is pointing to the right. Okay. And the reason the normal vector is pointing to the right is because this boundary is vertical going up and down. Okay. And so to cross over that boundary, you know, say you're just kind of walking, right? So you're walking in this box. Okay. In order to cross over that boundary, you have to walk in the X direction, right? Because that's the simplest, fastest way to cross over that boundary, to go in the X. Okay. And so when we take the dot product between V and N, what we're saying is that, you know, don't give me Vy, because Vy is the component that kind of walks parallel to that boundary. Okay. What we're saying is that, you know, when we're taking the dot product, give me Vx, right? Because Vx, this is the component that actually crosses over. Right. And that's important because, you know, whether something crosses into the cell or leaves the cell, you know, we have to keep track of it. Okay. Because that's going to affect, you know, how much of phi or how much of our solution is inside our cell. Okay. And so that kind of gives a good physical interpretation for these integrals. And this is true for both the convection and diffusion. Okay. And so what those integrals essentially do is they keep track of how much phi goes into and out of our cell. Okay? Okay. And so the main way or the main mechanism by which it keeps track of, what goes in and out is by just keeping track of what's happening at the boundary. Okay. And so that's what these boundary integrals represent. Okay. Because we're interested in how the quantity phi is conserved, within our system. Okay. And so by tracking, how much phi crosses over the boundaries, we can easily kind of keep track of, how much phi is in each cell at any given time. Okay. And the two mechanisms that can actually move phi, from one point to another, that can actually cross over a cell boundary, is one, convection, okay, and two, diffusion. Okay. And that's something that we know already, right? And so if you think back to when we discussed these quantities in finite differences, right? We talked about convection and diffusion as ways of taking phi, right, which is our solution, and transporting them to different regions in our domain. And so all this does is kind of just puts it in a different form. And so it puts it in an indirect form where we can kind of keep track exactly how much phi crosses into each cell or not. Okay. So this kind of goes back to the discussion we had last week, where fluid mechanics or fluid engineers, they love finite volumes because of this kind of feature of the integrals. It's very easy to have conservation of mass because whatever fluid leaves one cell, it's just automatically tracked as entering another cell. Okay, and so you kind of satisfy conservation of mass just by default, just by nature of the solution, which is fantastic, which is great to have. And so another term for these integrals, and so I'm not going to keep calling them boundary integrals where stuff crosses over because that's a mouthful. And so another way that we can think of these integrals is that these are often called flux integrals. And flux is a general term of how much of a substance or how much of a solution passes through a boundary. All right, and so that's kind of a key point to kind of remember about finite volumes, that they keep track of what leaves and enters each volume. Okay. All right, any questions on this? Okay. Actually, so I'm going to save this next part for for when we actually talk about diffusion. I think it'll make more sense there. Okay. And I'll leave the rest. I think it'll make more sense once we actually start talking about diffusion. Okay. So now that we have kind of a good introduction to what finite volumes is as a method, let's actually start applying that. Okay. And so if you remember, from our finite difference journey, the first thing that we did was we applied finite differences to a simple diffusion equation. And we're going to go through the same thing here. And so our first kind of big topic in finite volumes is how to do diffusion problems with finite volumes. Okay. And so let's first solve a simple diffusion equation, a simple steady diffusion equation with finite volumes, just to kind of get used to the method. Okay. And so if you remember, or another way that we can express the diffusion equation in finite volume format is to take the nablus. Okay, and so the diffusion equation is given by minus divergence of k gradient of phi. Okay, this is equal to q. Okay. All right. And so this is going to be our starting point. Okay. And so just like we did, with the general finite volumes, we're going to take this equation and we're going to integrate it over a cell. Okay. Okay. And so let's start with the 1D case, because the 1D case is often the simplest to do. Okay. Okay. And so I'm just going to take the expression above and express it as how it would be in one dimension. Okay. And so in one dimension, the divergence just becomes the derivative with respect to x. Okay. And then inside the parentheses, we have k times the derivative of phi, okay, is equal to q. Okay. All right, so I'm putting in this form just to kind of make the divergence theorem a little bit easier, but if you kind of remember from before, this was our diffusion equation, right? So our diffusion equation was simply a second order derivative with respect to x is equal to q. Okay. And then when we solve this with finite differences, we just took this derivative here. That's not what I wanted, but fine. Okay. And so we took this equation right here, and we just evaluated it, or we just plugged in its finite difference approximation. Oh man, I'm tripping on balls. My pen is multicolored now. Holy shit. There we go. Okay, and so if you remember, the way that we what this ended up with was something like this, right? Okay, so that's our second order derivative finite difference. Okay, and so when we manipulated this, in the end, and so after some manipulation, we ended up with the following. Right, so that's what we get when we isolated the left-hand side of the equation. Okay, and in particular, I want you to look at this left-hand side, and so this left-hand side is going to has coefficients of 1, -2, and 1, right? And if you remember, that's what we plugged into our left-hand side matrix. And so when we were forming our algebraic equations, when we were writing our MATLAB code for this, those were the coefficients that we plugged into our matrix. Okay? 1, -2, and 1. I want you to remember that because, we should hopefully get something very similar in finite volumes, okay? Because the underlying equation is not changed, right? And so this equation right here, is exactly the same as this equation right here, okay? And so in theory, because we're solving the same physical problem, then finite volumes should yield, a very similar equation, okay? Okay. And so I want you to kind of think about that and kind of keep that in mind as we, as we go along. Okay, any questions on this? Okay, all right, so let's go ahead and start applying the finite volume method. And so let's take our equation up here, okay? And let's integrate that over a cell. Okay. And a 1D cell, looks something like this. Okay, so this is kind of a generic 1D cell right here. And so the integral that we're going to perform, I'm going to perform between two bounds, okay? And so I'm going to integrate our equations between the left x index, which is xl, and the right x position, which is xr, okay? Where if we take the difference, we take xr minus xl, this is going to be our grid spacing, okay? And so the length of our domain is exactly the same as our grid spacing. Okay, so here's our governing equation. So we have minus k. Okay, we're assuming the k is constant, so I'm going to pull it out in the front. Okay, so there's our governing equation. And first thing we're going to do is we're going to integrate. Okay. Integrate with respect to x. Okay. And we're going to integrate between xl and xr. Okay. And so here we're going to need a little bit of help because these integrals are, we can't evaluate them because we don't know what the functional forms for these functions are. But what we can do is we can use our integration rules that we talked about earlier today. Okay. And so for this integral right here, we're going to apply a trapezoidal rule, or excuse me, thinking ahead again, I'm getting mixed up. So this one right here, we're going to use divergence theorem. And this integral right here, this one we're going to apply trapezoidal rule. Okay, and so on the left-hand side, we have divergence theorem. And so, divergence theorem is going to cancel out one of these integrals or one of these derivatives, okay? And we're going to end up with the following. And so we're going to have minus k, okay? Our integrand here is actually just d phi dx. And so this is going to be d phi dx, okay? Evaluated at the right boundary, okay? So this is going to evaluate at xr minus d phi dx evaluated at the left boundary. Okay. And this is going to be equal to, on the right-hand side, we're going to use trapezoidal rule. And so remember, trapezoidal rule, we take our integrand here, which is q. Okay. We evaluate that at the centroid of our domain. And so the centroid is going to be xc. Okay. And then we multiply by the length of the domain. And so the length of the domain is xr minus xl. Okay. Okay. So let me kind of box this for now. And so we'll pause here and we'll kind of evaluate each of these terms. Okay. I guess one thing we can do, since we've already defined it, this xr minus xl, this is the same as the grid spacing. And so we can plug in delta x for that. Okay. All right. Any questions on how we got here so far? Okay. All right. And so the right-hand side of this equation is more or less, more or less kind of already taken care of. And so, we've already applied a trapezoidal rule. And so we don't really need to worry about it anymore. Okay. Let's look at the left-hand side because this part is kind of it's kind of interesting. Okay. Okay. And so on the left-hand side, we have these two terms. Okay. So we have d phi dx at xr and d phi dx at xl. Okay. What these terms are is that these are basically our function derivative, right? The first order function derivative, evaluated at the boundaries of our cell. So that's true there as well. Okay. And so if I were to draw it out, and so here's our cell, I've kind of blown it up a little bit. And so the x coordinate here is xl, and the x coordinate here is xr. Okay. When we say d phi dx at xl, what I mean is d phi dx at this location here, okay, as well as d phi dx at this location here, okay. And so in order to complete this equation, we have to evaluate these two derivatives, okay? But here's the problem, okay? Remember, in finite volumes, we don't want to put our equation in terms of what's happening at the boundaries, right? Okay. And so we don't want to put our equation in terms of what's happening there. We want to put things in terms of what's happening at the cell centers. Okay. And so this kind of presents like kind of a tough situation for us. So we have two terms of value at the boundaries, but we don't want to know what's happening at the boundaries. We want to know what's happening at the cell centers. Okay. So let me do this. And so let me draw two neighboring cells. And so just to kind of make things consistent, we'll say this is XL and this is XR, okay? I'm going to label this, this cell in question right here. I'll call this cell C for the center, okay? The cell that's immediately to the right of this one, we'll call that cell big R. And the cell that's immediately to the left, we'll call that cell L, okay? So for the left neighbor, okay? And then the corresponding solution values at the cell centers will be marked with the squares. And so this will be phi C, phi big R, and phi L. All right. And so we brought in some neighboring cells into the mix. Right, because we're gonna need their help in this case. Okay, so let me go ahead and write these things down here too. Okay. And so the quantities that we want to compute are d phi dx at xl and d phi dx at xr. Okay. And let me note this too. And so the distance between the cell centers, okay, is going to be delta x, and it's going to be delta x as well. Okay. All right. And so the next step that we're going to do is we're going to use our neighboring cells. We're going to use their solution values to help us evaluate these derivatives. Okay. 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 So let me pause here for a second. So are there any questions on any of this so far? Okay. All right. And so to do that, let me go ahead and draw you another picture here. Okay. And so, when we go from cell L to cell C, our solution is going to vary, right? And so it's going to vary from phi L to phi C. Okay. So that's just kind of a normal solution behavior, right? So as you go from cell to cell, our solution is going to vary, right? And so visually, it might look something like this, right? So this might be phi sub C or phi sub L, excuse me. This might be phi sub C. Okay. And so one thing we can do is we can assume that the variation between those cell values is linear. Okay. And so if we assume linear variation, then of course we can find the slope of this line, right? Okay. And so the slope of this line will be phi sub C minus phi sub L divided by the space between them, which is delta x. Okay. And so that slope, because it's a linear line, that slope is going to be valid throughout the entire line. Okay. And so where else is that going to be valid? That's going to be valid at x sub L, right? Okay. And so we can use expressions like this to evaluate the derivatives at our cell boundaries. Okay. And so what we can do is we can take these slopes and plug in for boundary derivatives. All right, so let's go ahead and do that really quickly. Okay. And so first thing that we have here is we have a minus k. Okay. We have a d phi dx at x sub r. And so if we replace that with our slope approximation here, so it's be x sub r minus phi sub c divided by delta x. Okay. Minus d phi dx at x sub L. Okay, so it's going to be phi sub c minus phi sub L all divided by delta x. Okay, this is going to be equal to q times x sub c times delta x. Okay. Right. So let me go ahead and multiply both sides by delta x squared and divide by minus k. Okay. And so if we do that, the left-hand side, right, we have a phi sub r. Okay. We have a minus phi sub c and a minus phi sub c. And so it's going to be a minus 2 phi sub c. Okay. And we have minus phi sub L. So it's going to be plus phi sub L. Okay. And this is equal to minus q at xc delta x squared divided by k. Okay. And so what we end up with, we end up with this algebraic equation that we can use to solve for the cell center values there. Okay. And remember where we started. And so what we said was that in finite difference, we end up with the coefficients of 1, -2, and 1. Okay. And so for finite volumes, we get the exact same coefficients, right? And so this makes sense. And so this tells us that finite volumes should produce a similar solution for us as finite differences, which makes sense. Okay. Sorry. So I multiply by just regular delta x, not delta x squared. Sorry about that. Yeah, I wanted to cancel out the delta x on the bottom. Yeah, thanks for catching that. Mm-hmm. And so we end up with something that's very similar to finite difference. You would almost say it's almost identical. It's almost identical, but not quite. Okay. All right. Any final questions on this? Okay. All right. And so on Wednesday we'll pick up here. Okay. And so I wanted to get to this punchline, before we end today. So I thank you guys for staying a little bit extra. And then on Wednesday, we'll actually start to solve these and actually see how it actually works. So thank you everyone for tuning in today. I know this week is tough to focus because it's right before spring break. But I thank you guys for coming as usual. Right? So have a great rest of your day, and I will see you all on Wednesday. Oh, if you're here in person and you haven't picked up your midterm, I brought them here, so you can come pick them up.
Friday?
Yes, that's right.
When will we introduce the project?
Wednesday, we'll talk about the project.
Okay.
The project's not going to be due until the very end of the semester.
So it's project is due in the final week or before the final week?
After finals.
After final.
Yeah, so it'll be the Monday after finals.
So we can do the project. We can still have time after during the final week.
Yes.
Okay.
Yeah, we'll talk about it next time. So I think the due date's May 23rd or something like that.
Okay.
And so it'll be after.
Okay. Thank you.
Yep. Mm-hmm.
Thank you.
Thanks, Evan.